I'm very happy to introduce our first tutorial speaker today, Emma Brunskill from Stanford University. Emma is one of the stars of reinforcement learning. She got her PhD at MIT and spent some time at Carnegie Mellon University before joining Stanford. And one of the most exciting things about her work is that it actually has a lot of interesting applications in fields like education, which informs both the theoretical work that Emma has done as well as the kinds of algorithms that she's thinking about. And so we're very excited to welcome her here and to hear about these algorithms.
Thanks, Dorna, and I'm really excited to be here. I know this is basically the middle of night in terms of computer science time, so thank you guys for coming out. I'm also happy for this to be fairly informal, so feel free to interrupt me with questions. I'll give you a little bit of a background in a second of what I expect in the audience in terms of background, and it's generally very open to any level of background. And then we'll have a break halfway through so that we can get a little bit of coffee. So I'm really excited to be here to talk today about reinforcement learning for the people and by the people. And I'll just quickly credit that Nika Hagtail has been using this for some of her work for machine learning. And I think this notion of for the people and by the people is very exciting. So there's been some really amazing progress in reinforcement learning so far. And I probably don't have to tell anybody in the audience about it. In particular, in things like video games, we're starting to have human-level performance on Atari games, or better than human-level performance. Of course, the recent success of AlphaGo Zero is a game changer, literally. And there's also been some really amazing work that's going on in robotics. But one of the things that I'm personally really excited about in terms of machine learning and artificial intelligence in general is thinking of using artificial intelligence to amplify human potential rather than as a way to replace humans. And when we start to think about how these systems can interact with people, how reinforcement learning systems can interact with people, there's all sorts of differences and challenges that come up, as well as a lot of opportunities. And that's what I'm going to be talking about a lot today. So the tutorial today will be split into roughly 3 parts. I'm going to do a short reinforcement learning introduction, sort of RL 101, and then I'll talk some about RL for people, and then some about RL by people. So this is just a quick summary of, in terms of things that you might be interested in and where these might fit. So if you are totally new to reinforcement learning, I hope that I could give a really brief introduction to reinforcement learning. I know that a lot of people are starting to get really excited about this field, and as someone who's been working on it for over a decade, that's really, really exciting to see. So I'm going to spend maybe about 10-15 minutes just talking about a brief background, which will be a refresher for many of you. And then if you're interested in understanding what are the hard technical challenges that come up when we start to try to do reinforcement learning for people-facing applications, things like healthcare and education, that'll be the main second section of the talk. And then at the end, I'm going to talk about how can people help RL systems? How can we have human-in-the-loop systems where people are actively trying to help these systems do better? I'll just give a brief caveat. Of course, anything that's only 2 hours is necessarily woefully incomplete. I'm definitely not going to try to cover all of the particular domain-specific ways for tackling these problems. And in particular, I'm going to focus very much on the reinforcement learning setting and the new technical challenges that come up when we try to do reinforcement learning for these type of settings. I'll add some more references afterwards. If you have other critical ones you think I've missed, I'm always happy to learn about them. So reinforcement learning for people. This is a variant of a standard diagram that many of you might have seen. You can think of there being, say, for example, an intelligent tutoring system that is interacting with a person. And the way that the intelligent tutoring system works is it provides, say, an activity to the student, like a math exercise, and the student does that activity and gives some response back. Now, of course, this happens in real-life human tutoring as well, but it's something that we could think about automating. And we could also imagine getting some form of reward signal in this setting, things like whether or not the student passed the exam. Now, this comes up not only in education, but in a number of other cases where we can think of the environment that the agent that is interacting with as essentially a person. So if you think about something like customers and trying to maximize lifetime revenue, you can think of a computer or an agent trying to suggest products, and then the person can either click on those products, they can choose whether to buy them, and you can measure things like long-term revenue. In general, in reinforcement learning, we have this sort of continuous cycle of taking actions and observations and getting some reward. And what I'm going to do now is give you sort of a brief introduction to some of the framework of it. I'll also just say that in my own work, as Dorina mentioned, I do a lot of work on reinforcement learning for automated education systems or for assistive education systems. And a lot of that work tells us that it is extremely ineffective to lecture at people. So I apologize for the rest of this time for completely violating my own principles. So now we're going to do Reinforcement Learning 101. This is basically the summary I'm going to cover. We're going to start off with what a Markov decision process is. So a Markov decision process is a stochastic decision-making process where an agent gets to make a series of decisions. So they're defined as a tuple, where we have a set of states S, a set of actions A stochastic transition or dynamics model, which reflects the probability of reaching another state S prime after taking action A in state S, a reward model, which can either be defined as a function of states and actions, or states, actions, and next states, and maybe a discount factor gamma or horizon H. And just to give me a little bit of a sense, can you raise your hand if you've already seen this before or taken a class on machine learning? Okay, awesome. So everybody who's actually here this early in the morning is pretty dedicated, so that's great. Now, just as a quick refresher for maybe the one or two people that didn't put up their hands, a policy in this setting is going to be a mapping from states to actions. That's going to be sufficient because of the Markov assumption, which means that the current state is sufficient for us to be able to make optimal decisions. And an optimal policy is the one with the highest expected discounted sum of future rewards. In the partially observable MDP case, it's very, very similar, except for now we're going to assume that we only get observations instead of direct access to the state S. And so we'll also have an observation model, which tells us about the probability of an observation given an underlying latent state S and an action A. In this case, we often think about having policies that are mappings from histories, which is a series of states and actions and or observations, actions, and rewards to the next action we want to take. And again, our primary concern is going to be to get a policy with the highest expected discounted sum of rewards. So I'm just going to say briefly what policy evaluation is. Once you're given a model, an interesting thing might be able to do is to evaluate the value of a particular policy. So you might want to just know how good a policy is. And one thing you could do is if you're given a model, which is that transition dynamics and reward model, you could just treat it as a simulator. This theme will come up again later. So you could do things like Monte Carlo rollouts and average them, but because of the structure of the problem, we can do something much smarter. We can use dynamic programming to solve it. So you could imagine initializing the whole state space to 0. And right now I'm not dealing with function approximation cases like deep learning. I'm just thinking about a tabular setting where you can write down the value of every single state. And you can iteratively update the value because the value or the expected discounted sum of future rewards you get from a particular state is exactly equal to the immediate reward you get plus the discounted future rewards you get from that point onwards. Now, it turns out that if you want to do planning and you want to actually compute the optimal policy, then you can do something very similar by using the Bellman optimality equation. And the Bellman optimality equation says that the value of a state is exactly equal to the immediate reward plus the discounted sum of future rewards by following the optimal policy. We can also define the state action value as being the immediate reward we get plus the discounted sum of future rewards we get acting optimally after first starting with action A. And from these equations, we can also extract the optimal policy. So I bring up this setting, which is not reinforcement learning, because this sort of illustrates one of the things we can do once we have models. Now, in reinforcement learning, we normally still assume that it's a Markov decision process, though often we also think about POMDPs. But the key issue is that we no longer know how the world works. So we don't know the dynamics, and we don't know the reward model. And yet we still want to be able to take actions to yield high reward. So there's this figure from David Silver from one of his lectures that I like a lot, which sort of talks about the three common approaches to reinforcement learning. And one of them is model-based, another one of them is value function-based, and the third is policy. And of course, there's a lot of intersections between these three. But I like this a lot because I think it explains the sort of different viewpoints we can think about when we try to start tackling reinforcement learning and the relative strengths and equivalencies between them. So if we do something like model-based reinforcement learning, we're still assuming we're in an MDP, and as we act in the world, we're going to observe states, actions, and rewards. And we can just use any form of machine learning method to try to estimate a model of the dynamics and or the rewards. So this can be things like maximum likelihood. There can be lots of different techniques. We're essentially just trying to solve predictive problems, predicting the reward and predicting the dynamics model. But once we have that, we can map ourselves back into planning land, because now we've created an estimate of the MDP. We might in fact create many estimates of the MDP, and now we can treat ourselves as if we're just going to do planning with one or more of those sets. So that's one of the advantages of model-based reinforcement learning, is that once we get a specific model, we can apply all the sort of tricks that we do with planning to that model. But one of the nice observations very early on in reinforcement learning is that we don't actually have to be model-based. We can be model-free. And Q-learning is perhaps the most popular approach for this. So the idea in this case is we're going to initialize a state action value for every state action pair. And again, this can easily be extended to the deep reinforcement learning setting. And the idea is that as we act in the world, we're going to do a couple things. The first is that we're going to calculate the temporal difference error. And the temporal difference error is essentially the difference between what you observe and your current estimate of the long-term expected reward. Now, it's just a sample of this. So what we're going to do is we're going to say, what was my current estimate of the state action pair? And then what was the actual immediate reward I get, plus the discounted sum of future rewards I'd get from that S prime onwards. And that gives us a difference that we can compare those two estimates, and then we can try to move our estimate of the state action values to be closer together. It's making a number of important assumptions. It's leveraging the Markov property. This works because we know that the state action, the state is Markov. And it also bootstraps. And what that means is that we didn't actually wait to see how much reward we got till the end of the episode or the end of time, but instead we're going to use a proxy of the expected discounted sum of future rewards by whatever our current estimate is of the action value function. So we do this, we compute this TD error, and we use it to update the estimate of the state action values, which can then sort of slowly move our estimates to be closer together. Now, this is very computationally cheap, and one thing that I should mention is that in a lot of the things I talk about today, I'm going to be very interested in data efficiency. This is a pretty big departure from a lot of the work that's been going on right now, and I'll talk about why that might be important later. But in this case, one of the reasons why Q-learning was very interesting and continues to be very interesting is because it's very computationally efficient to do these updates, but it only propagates the experience one step. Now, this can be remedied by doing things like experience replay, which have been very effective recently. Now, the sort of third circle in that slide I showed you just before is that we can do direct policy search. So again, we don't necessarily need to have a model in this case. What we're going to do is we're going to treat it as sort of a function of optimization problem, that we have some space of policies and we just want to find the best policy in that space. And we can typically do things like do stochastic gradient descent to try to search within that space. And this has been very, very influential, and I'll also give some pointers to other tutorials on this later. So these are sort of the three most common approaches to reinforcement learning, and many of the big advances in them have come between the intersections of some of these different approaches. Now, the other sort of thing in my RL 101 that I want to mention is that there's also the key issue of exploration versus exploitation. One of the key challenges in reinforcement learning that makes it so different than supervised learning is that the way we learn about the world is by acting, which means that we constantly get censored data. We don't get to find out what would have happened if we took a different action. And so then there's constant trade-off between learning more about how the world works, as well as using that knowledge to try to maximize reward. Okay, so now I'm going to continue by talking about reinforcement learning for people-focused applications. So as I said, there's been a lot of progress in reinforcement learning so far, but there's a number of differences when we start to think about having automated agents that are interacting with people. And I'll first start with two of the key challenges. The first is that in a lot of the video game situations, it's been very easy to simulate how the world works. This has allowed us to have agents that play for hundreds of millions of episodes. And that's really terrific. It costs us some amount of computation, but it's a very feasible thing for us to do. But in the context of people, that's not possible. First of all, there's only a finite number of people. And second of all, they're very hard to model. So if we want to do things like build models of patient physiology or student learning or customer behavior, we just don't yet have really, really accurate models that would allow us to completely model how people would behave and build very effective simulators. Now, robotics is an interesting other case, but where often things can be challenging to write down precisely. But again, we often have pretty good physics models. And so often it's possible in the robotics case for us to do a lot in simulation. Whereas again, because it's very hard for us to write down good models of human behavior, it means that it's both high stakes. We don't want to sort of take a lot of risky actions or fail to teach 1,000 people's fractions, as well as being hard to model. So today I'm going to talk about 3 of the technical challenges in reinforcement learning for people. The first is going to be sample efficient learning. The second is going to be talking about what do we even want to optimize for these type of applications. And then the third is going to be thinking about how do we do sort of batch, purely offline reinforcement learning. So just before I get started, let me just tell you a couple of the different types of applications I mean here. So one of the things that I think about a lot is how do we scale up effective and engaging education. And in these situations, we often are having students interact with educational games or online tutoring systems. And what we want to do in this setting is to be able to quickly and continually learn how to teach people better. So we want these sort of continually evolving systems. And we want to be able to adapt to every single individual student. And very similar challenges are coming up in things like personalized healthcare. So how could we accomplish this? How could we have really radical sample efficiency? And again, for some of you coming over from other sorts of communities, what I mean here by sample efficiency is that I want to need very, very little data, both in terms of the number of individuals I interact with, as well as within an individual, how long, say, I'm teaching them for, in order to start getting good performance. So I both don't want to have to teach many students before my system is good, and also for individual students, I want to do well. So if you imagine having access to a lot of different students you're trying to teach or a lot of different patients, we can start to think of this as a transfer learning problem. And there's a lot of different trade-offs and strengths and limitations depending on how we model the individual instances that are coming. So when I say transfer learning in this case, you can think about teaching each individual student as a separate MDP or POMDP. And one approach would be to say that all of the students coming in are completely different. Now, that would be beneficial because it would allow you to get very, very good policies for each individual student because you can completely customize. But on the downside, you're not going to be able to share any data. On the other hand, you could assume that all students are exactly the same in terms of their dynamics and their reward, but then you would lose the opportunity to personalize across students. So one of the initial assumptions that we made in our work, and I'll talk about a number of other people's related assumptions, is to assume that there's a finite set of groups. So this is going to allow us to hopefully get some of the benefit of doing partial personalization to individual people while still getting strength by sharing data efficiency across individuals. So how might this work? We can think of this as being sort of a multitask or lifelong reinforcement learning problem. And in this simple setting, let's imagine we just have 3 different MDPs. Now, all of them are going to share the same state and action space, but they might have different models. They might have different dynamics models or reward models. And the way we're going to think about this is that when we interact with a new task, it's going to be sampled from this finite set of MDPs. And then we're going to do this a series of time where in each MDP we get to act for a certain number of steps, say 8 steps. This could also be, a discounted horizon problem. And then we again sample from that set of MDPs. And so this is a tutoring system that's teaching a series of students, or a decision support system for healthcare, which is interacting across a series of patients. But one of the challenges is that people don't come in with labels on them saying that I am a particular type of student or a particular type of patient. And so the first thing is that these sort of identifiers are latent. The other challenge is that we don't typically know what these latent classes are to start. We don't know this finite set of MDPs nor their parameters. And this generic setting can capture a number of different scenarios of interest. So one of the ways that we've proceeded at trying to make progress on this is by treating it as a latent variable estimation problem. There's been a lot of progress in doing better clustering and latent variable estimation over the last decade. And one of the most exciting things to me has been that we've moved from having techniques that often work really well in terms of expectation maximization, but lack formal guarantees, to approaches like tensor decomposition and other approaches which actually can give us formal bounds on how good are those clusters that we extract. So a lot of the work that we've done has looked at building on that work so that we can actually get provable guarantees on us being able to recover this latent structure and then using it to provably speed learning for new instances. Now, because we've been focusing on the theoretical side of this, most of this work has been highly impractical in terms of it's focused on giving us provable speed-ups in learning, but not in developing practical algorithms. Now, one of the exceptions to this is thinking about it for some work in contextual bandits, where we've been thinking about this for things like product recommendations and trying to leverage large amount of recommendation data in order to speed up learning for new individuals. So that's one particular assumption. We assume that there's just this finite set of groups, but of course that's somewhat limiting. We don't generally want to assume that there's only 3 or even a finite set of individuals in the world. And some of the early work that's tried to think about there being this structure across tasks in a sample-efficient way is Bayesian hierarchical multitask learning. So this was a framework that was developed by Alan Fern and his colleagues about a decade ago. And the idea in this case is it was sort of this hierarchical multitask process where you could have different types of tasks that had shared structure, but you could have, in fact, an infinite number of tasks. And this had a number of very nice properties in terms of being able to speed learning and get a lot of shared structure across tasks. So in particular, in some of their early work, they looked at things like maze learning and other sorts of small settings. And they found that they could get much improved reinforcement learning and sped performance in these settings by leveraging this hierarchical structure. So this was really encouraging empirically. There weren't formal guarantees on the performance, and it wasn't quite clear whether or not this would scale really well to really complex situations. So another framework that has been introduced over the last few years that sort of extends this and thinks about it again for sort of less hard, rigid situations of just one of M situations is the hidden parameter MDP work from George Conadaris and Finale Joshi Velez's lab. And the idea in this case is, again, we're going to be moving towards allowing all tasks to be different, so all patients to be different or all students to be different, but we again want to get a lot of sharing across the different models. And you'll notice that all of the work that I've talked about so far in the sample efficiency case is in terms of these underlying models. I'll talk about some other approaches that doesn't necessarily have to make that particular assumption shortly. So the idea in this setting is that we're going to build models of the dynamics, and we're going to assume that there's this sort of continual parameterization with a shared basis function. So what you can see here in this graphical model is that there's a finite number of underlying task basis functions, essentially, to describe the models. And then what we can do to create a particular task is that we weight these different models. Now, this initial approach was using Gaussian processes, as well as using things like infinite Indian buffet processes, so we could determine the number of hidden tasks in this basis set automatically. One of the exciting things I've seen recently that they're going to be discussing at this NIPS is looking at how do we extend this to much more complex models. So one of the challenges with Gaussian processes is that even though they're very flexible ways to model the dynamics, they don't scale very well as we start to have high-dimensional state spaces. And compared to that, Bayesian neural networks are very promising in terms of new types of techniques that we can use that could be much more scalable and yet still allow us to be specific about our uncertainty over how the world works. So Finale Joshi and George Conadaris and Taylor Killian have developed a new approach, which is using sort of a weighted set of Bayesian neural networks to represent the dynamics, which again is going to allow us to have this shared basis function across many different individuals or tasks. And one of the most exciting things to me about this recent paper is that they're looking at how we can use this to do much better things like HIV treatment simulations. And so what you can see in this graph here is a number of different lines where we're comparing across either making model-free assumptions or average model assumptions, or allowing there to be different models for every single individual, versus trying to start doing this shared structure. And one of the important things to notice here is that each, at least to my understanding of this graph, every single episode here is actually just an individual patient. And so that's really what we want. We want to be able to very quickly learn across patients and then have high performance for every single patient, even though each of them might actually require very different treatment strategies. And so that's really, really exciting and promising to me in terms of seeing how could we actually have these radically sample efficient methods that would allow us to sort of span between data sharing and personalization. So another type of approach to getting sample efficient online reinforcement learning is policy search. And I probably don't have to tell anybody here that policy search is one of the most popular methods in reinforcement learning right now, and it's been hugely influential, particularly from a lot of the terrific work that's going on at Berkeley, but really many places. And I encourage you to check out the NIPS tutorial from last year if you hadn't seen this already. Now, interestingly, policy search is not always associated with data efficiency, but it can be a very nice and easy place for people to be able to put priors in about how they think, what sort of policies they think may be effective. And so if we can have very, very restricted policy classes, then that can start to be very sample efficient. So in particular, we can think of policy search as simply function optimization, where we have a set of policy parameters, and there is some associated value with each of those particular set of policy parameters. And if we use things like Gaussian processes, then we can explicitly represent our uncertainty over what is the potential value of different types of policies. Now, most of the work that goes on in policy search treats this as sort of a gradient descent problem. And a lot of these methods can leverage the particular structure of sequential decision making in these types of algorithms. This is the majority of the policy search algorithms we see today. But one of the limitations of them is that they typically only find local optima. Now, in some domains, that's completely reasonable. In other ones, we would really like to be able to find much better optima or even get guarantees on global performance. So one of the nice things of framing this in this sort of Gaussian process way, or thinking of this as Bayesian optimization, is that both we can reason about the cost of each of the evaluations in order to try to find that best policy set of policy parameters. And they also have this nice guarantee that eventually we are guaranteed to find the global optima. But one of the challenges is that a lot of the Gaussian process work originally and the Bayesian optimization frameworks were not developed for the reinforcement learning or sequential decision-making setting. So they often ignored a lot of the structure that we typically use in Markov decision process planning and learning, which could lead to much worse sample efficiency than would be possible. So one of the things that we wanted to do in some of our work, and one of the things that we've seen in some of the other work by Alan Fern and his colleagues, is how do we leverage this Markovian structure when we're doing policy search using Gaussian processes or other types of techniques that can explicitly represent our uncertainty over the estimated policy values. So what we would like to, one of the reasons we would like to use these in general is that it allows us to be very agnostic to how the world works. All we're trying to do is to find the best point in this policy space. And particularly in the case where we may not have very good models, this can be very important. So what I've put up here is some recent work that we have on doing policy search for optimal stopping problems. In an optimal stopping problem, it's an extremely simple form of a decision process where all you're trying to do is to decide whether to halt the process or not. So you can think of this for things like if you buy a stock, whether you should sell the stock or you should keep holding on to it. Similarly, in the context of education, you can think of figuring out how much practice does a student need until you decide that they've mastered the material. So one of the things that you can see in this plot is that we're looking, on the x-axis, we're looking at different budgets of collecting existing data, trajectories essentially where we stop at the very last possible moment. And the reason that we do that in this case is because it allows us to do off-policy evaluation, which I'll talk a lot more about later. But one of the insights that we had for this case is that if you, for example, hold a stock for a year and you get to observe every day what the price was, then you can actually retrospectively evaluate what would have happened if you had sold it at any other time, which means that you get a really efficient way to try to do off-policy evaluation. Because if you have one trajectory that goes to the last possible time point at which you could sell something or at which you could halt the process, you can actually evaluate any other stopping policy from that one trajectory. So the nice thing about this is that we can really reduce the amount of data we need. But what we're showing in this particular graph is on the x-axis is how many trajectories we have, sort of how many full times we've allowed the process to go to the last possible stopping period, and then using those to do off-policy evaluation and try to find a good policy, using also Gaussian processes in the background. And one of the things that I want to highlight here is that if you use model-based approaches for this case, here where we're using sort of a simple student model, that if your model is wrong, then you could do very badly if you have model mismatch in your process. And I'll talk a lot more about that issue later. But if the way that you're modeling the world is different than the way the world actually is, then you're fundamentally limited by how well you can do. And that's what you can see here with sort of the middle line with the sort of solid circles. But at the bottom, you can see how we can do using policy search. And in this case, even if the model is wrong that we're using inside of our sort of parameterized policy, it can even sort of include some policy parameters within it, it can do the best it can possibly within that policy class. So we also looked at this for some other types of domains that would be people facing, things like how could you figure out when to buy an airline ticket, a challenge that all of us had to face to come here. And in these cases, again, we can see that we can get a very big benefit in terms of the amount of data we need by leveraging the particular structure of this problem. And so we could get substantial data efficiencies compared to some of the generic bounds for policy evaluation that were developed by Inge and Jordan in 2000. However, one of the problems here is that we were using Gaussian processes to do this. And as I mentioned before, Gaussian processes don't scale very well to high dimensions. So I think there's still a lot to be done to try to figure out how can we get some of the benefits of policy search in terms of their flexibility and allowing us to really represent any type of function if we use things like deep neural networks, combined with the potential benefits of things like Gaussian processes and Bayesian neural networks, in order to get explicit representations of our uncertainty and yet be very data efficient. And I think that Bayesian neural networks are one of the really promising places to do that. Now, there's also been a lot of other work in sort of the direct policy search techniques, where we're again making strong assumptions of what that policy class looks like, but aren't necessarily modeling it in a Gaussian process or neural network way. And in particular, there's been a number of papers that think about sort of a mixture of experts approach, where what you can get is either because you've been doing lifelong learning or because you have access to a set of experts, that we can get a finite set of policies to try to speed learning in a new task. So you could imagine that you would have something like a number of different people think of the best ways to teach a student or different ways to treat a patient, and then what you try to learn over time is which of those is most appropriate for the current patient or the current student. So there's been a number of different techniques to try to do this. Some of this has been looking at it from the theoretical side, and others of them look at them from the practical side. One of the challenges here is being able to go beyond the performance of the input policies, as well as when to identify when none of them are sufficient. And I think that's a challenge that comes up over and over again in our work, at least, on reinforcement learning for people, which is how do you diagnose the unknown unknowns? How do you know when your policy just isn't reaching the performance that is needed? And what are the critical assumptions that is making that the problem? There's been other work that tries to, again, do something that's a little bit more similar to the hidden parameter MDP work, but for policies, where we're thinking of there being a shared basis set to represent policies. So again, this is specifically for the multitask setting. And this is some of the work that's come out of Eric Eaton's lab. And the idea is that we're going to be able to represent our policies by a shared set of bases, and then we're going to be learning for each individual task how to weigh those basis sets. So they've been doing this and have shown that they can get some really nice results in different control tasks where they actually share data across very different types of tasks. So for those of you who do things like robotics research, you'll be familiar with the cart pull problem. And some of the work that Eric Eaton has done has looked at, sorry, the citation on this is incorrect, that should be Eric Eaton's, but some of the work they've looked at there is looked at how would you generalize between performance on something like cart pull to performance on something like a helicopter. And in some ways, this is really the dream of transfer learning. How can we leverage things that seem quite different to actually still speed up learning in new tasks? So they've also thought about how you can leverage other forms of shared structure, starting to look again a little bit more in the hidden parameter MDP sense of saying how can we look at sort of shared feature structure, doing shared feature representational learning, as well as policy structure in order to get significant gains in performance. Again, this work has been done not as much in the deep learning setting, and so how we scale this up to take advantage of the deep learning models is not yet clear. On the other side of this, of course, there's been this huge amount of work on the policy search case for deep learning models. And in particular, a lot of the work that's been tackling this for robotics tasks and thinking about sample efficiency has been coming out of Sergey Levine and Peter Abeel's work, as well as Chelsea Finn up at Berkeley. And so one of their recent papers from ICML has been thinking about this for multitask learning and really getting very efficient performance by trying to directly learn representations in the deep neural nets that are going to allow us to speed learning in related tasks. Now, in these type of tasks, it can range, but it can often be things like continuous control tasks, where you might have slightly different parameters. So you can imagine things like you have slightly different lengths inside of a robot, or you might have slightly different weights, or things like that. Now, one big challenge that comes up in all of the settings is that we need to have shared structure. And we'll be making some assumptions that there is shared structure across these tasks, which means that if there isn't, there's the potential of negative transfer, which is what happens when you try to transfer information that is actually not relevant to the current task and you hurt performance. And again, that's another one of the very big challenges in this area of figuring out if you assume structure and that structure isn't present, how can you still be robust enough to recover performance and not suffer too much? Now, most of the methods that I just mentioned are trying to speed online learning in a new task, or trying to speed up how quickly we can learn across a series of tasks, say a series of patients or a series of students or a series of customers, but they're not making guarantees on performance for a single task. So I'll talk about more the type of objective that we want in the next slide, but just for references, here's a number of different references that are talking about how we do this much more sample efficient reinforcement learning. So as I was starting to say, I think in many of these cases, we want to move beyond expectation. And there's been a number of exciting works in this direction over the last few years. So if we're interacting with people, even if the agent may in fact interact with many people, that individual may only experience that one trajectory. You can think of this as why things like insurance work. Insurance works because the insurance company is trying to optimize across everybody, whereas individual people are risk sensitive and they want to make sure that their one trajectory doesn't have too bad of a negative return. So when we start to think about creating RL agents that interact with people, if we want them to be appealing to people, then they might also want that the policy that the agent is developing to also be sensitive to the risk sensitivity of the individuals. So there's been a number of different recent ideas on this, thinking about how do we move beyond policies that are trying to maximize expected return to trying to build policies that are risk sensitive or robust. And this robustness can be to the stochasticity and the dynamics. It can be robust to the uncertainty in the parameters during reinforcement learning. And it can be parameterized in a number of different ways. So there's things like conditional value at risk, which there's been a number of different papers at, including by a lot in Shai Manor's lab, where we're trying to directly optimize for percent of the worst case scenario. So I think that moving towards these type of frameworks where we're thinking about not just maximizing expected reward, but thinking about these other type of parameters is very important. And in some cases, we may have constraints. There's a lot of different types of objectives we might want in these settings, but it allows us to start thinking directly about new forms of performance guarantees. Similarly, the first set of papers that I just mentioned is thinking about getting policies with ultimately different performance, but we also might want to change the reinforcement learning process itself. So there's also been a lot of interest recently in safe exploration, particularly in robotics, because if you don't explore safely with robots, you can break them, as well as when we start to think about autonomous driving cars, things like safe exploration is very important. Now, of course, this is something, safe exploration and safe performance is something that has been tackled extensively in the controls community for many years, and often we can have formal guarantees on the resulting performance of a system. But some of these have been very conservative and haven't been updated with additional data. And so I think some of the exciting work that's happening right now in safe exploration is moving between these two fields. Things like reinforcement learning that typically have been very data-driven, but may not have had safety guarantees in the past, to other forms of formal methods or control systems where we can make very strong guarantees about safety, but maybe haven't been able to reach the potential performance that is possible because of being overly conservative. Now, almost all of these papers, when they are providing at least guarantees or even high probability guarantees on safety, are going to have to make strong assumptions about the parametrics of the world. As a simple example of this, you could imagine that if you want to try a new action and you want it to be safe, if you don't have any guarantees on how the world works, then anything could cause you to sort of fall off a cliff. But if you can make smoothness assumptions about how things work, about how smoothly the dynamics of the world can change or how smoothly the reward function can change, then one can start to have formal guarantees that allow the agent to slowly expand its space of safe behavior and can end up with having sort of provably safe exploration. So another thing, I mentioned a lot of sort of some of the challenges in reinforcement learning when we start to deal with people, but there's actually also a benefit, which is great, which is that when we think about robots that are acting with people, or we think about video games, we have access to some data, but not a lot of data, particularly in the robotics case. We don't all have 10 robots in our home that are constantly generating data, but we do have a lot of data about people. We have a lot of data about consumers, we have a lot of data about patients, and we're starting to have a lot of data about students. And that's a real opportunity for us to leverage the data that's already being collected, that observational data or sometimes semi-randomized data, and use it to try to make better decisions. And that's been something that we've been doing a lot of work on, as well as a number of other of my colleagues. Now, the work that I'm going to talk about right now is going to be entirely in the offline setting. So the idea is that this data is being collected anyway, or it's been collected for some other purpose, and what we want to do is use it to do reinforcement learning. So just as a concrete example, imagine that we have a set of classrooms, the A classrooms, where in them the students first received an activity on a computer, and then they received an activity on a chalkboard, and those students got a score of 95 on a test afterwards. And then we have some other set of classrooms, the B classrooms, where first students do an activity on a chalkboard, and then they do an activity on a computer, and then they get an average score of 92. And what we want to do is figure out a good new policy for a new student based on that experience. And so what would you do? Or what questions do you think we should ask in order to answer that question? Yeah. Great, so one suggestion was, I didn't tell you what type of students A or B were. A could have been college students and B could have been kindergartners, and I didn't tell you what the new student was. So one thing is to sort of understand what are the populations of individuals in each of these groups, as well as what is the characteristics of the new student. Are there any other things that maybe we should ask in these type of cases? Yeah. Yes, how many students, right? So if I told you there was one student in classroom A and one student in classroom B, you probably would say, well, we can't tell anything about this. That's not very significant. And so there's a whole bunch of issues that we need to think about in terms of this data that's being collected. Now this issue, which I'm going to call batch RL or counterfactual reasoning, and in fact there's a workshop on the what if reasoning and what next reasoning later this week, comes up in many, many domains. So for example, in a current collaboration with Siemens, we're looking at this for conditional maintenance scheduling. So you could imagine that you can repair equipment in different orders and at different time periods, and you can see what their costs are, and you would like to figure out the most cost-effective way to do maintenance. And in things like patient treatment ordering, you can see from your electronic medical record systems what types of treatments people are getting and when. And of course, those treatments may only be partially overlapping, as well as there may be lots of different characteristics of the individuals that are getting those treatments. And then for a new patient, you want to figure out what to do. So there's a number of reasons why this is a really challenging problem. One of them is because we have counterfactual reasoning. So as was just brought up, the people in classroom A and the people in classroom B are not the same by definition. We don't have any copies of people with exactly the same upbringing and same genetics. They're both classroom A and classroom B, and they may be wildly different. And I didn't tell you what would have happened in classroom B if they were to get the same interventions as in classroom A, or to get the same policy. And this is always an enormous problem with counterfactual reasoning, because we have to figure out what could have happened when we can only in fact take one series of interventions for a situation. Another big challenge is generalization. So in this case, it's pretty simple and easy because there's only 2 interventions, and I'm only showing you that we're going to do them twice. So it's a small set of policies. But in the general case, we would like to not have to enumerate all of the possible policies and then decide among them, but we'd like to be able to generalize. We'd like to say, well, I have experience of doing computer then chalkboard, and chalkboard then computer, so what can I say about what computer and computer would do? So this issue of counterfactual estimation, as I mentioned, is an enormous field of research. It comes up in things like statistics and economics and healthcare and many, many other areas. And so the distinctions that I'm going to make today when I talk about this work is focusing on it for the sequential decision-making problem. So thinking about this really is, how do we do it when the underlying task is reinforcement learning, where we want to maximize over a series of time steps, a series of decisions, the outcomes for an individual. So in particular, this is the sort of framing of the problem that I'll be talking about for the rest, which is we have this batch data policy evaluation problem. So we have some data on decisions and outcomes that was collected from the past. And then we have a set of candidate policies. This could be an infinite set of policies. We could do things like gradient descent over this. But imagine for right now that there's just a finite set of policies that we're interested in. And what we want to do is figure out how good each of these policies are. We want to just get their expected performance in the future. And again, we can customize this type of objective to if you want to get single trajectory guarantees. But for right now, let's just imagine we want to compute the value of each of these different policies. And then in addition to this, we might want to do policy selection. That given this candidate set or this infinite set, then we want to decide which one we're going to deploy going forward in our decision support system or in our intelligent tutoring system. So there's a number of different sort of desired characteristics we might want if we're doing batch reinforcement learning for people. We may be in the situation where we only care about policy evaluation. We may not be doing policy selection. We're just trying to evaluate, how effective a particular intervention was or current policy. We might want things like asymptotic guarantees on the estimators, particularly if we're coming from a statistics perspective. We may want to make sure that the estimators are consistent or that they're asymptotically normal in terms of their confidence intervals or other properties like that. We might want to measure the confidence in how good are these estimates, because we are going to be making decisions, or we have to go back to our boss and say, I'm sure this system is going to be better for all of the students in your district. We may just want to measure the confidence in the policy itself, but not care about the values. And Joelle Pineau and Susan Murphy have some nice work on this, on looking at how confident are we that this is the particular correct policy in the case of healthcare, as opposed to perhaps flipping. We might just care about good performance going forward. We might just want to make sure that we're going to have a good policy going forward, but not care about theoretical guarantees. And we might want to be robust to any assumptions we're making during the estimation process. Again, there's a lot of really exciting work on off-policy policy learning, but most of this work has focused on the online setting, where we are doing off-policy evaluation, but the agent is still getting to make decisions in the world. In contrast to that, the work that I'm talking about right now is when we're stuck with the data that we have, and we're going to have to do the evaluation only with that data, and where we might care about the policy that we select based on it. So this problem first came up to us in the context of an educational game. This is Refraction, which is a game to teach students about fractions. It was developed by my colleagues up at University of Washington in Zoran Popovich's lab, and it's been played by about 500,000 students. And in this game, students split laser beams to try to learn about fractions, and there's a number of different levels they can go through, which cover different types of fractions as well as different types of spatial reasoning. And we had a question in this case, which is how do we figure out what level to give to the student when in order to maximize engagement in learning? And in this case, we had access to about 11,000 students' data, and we wanted to figure out how to solve this problem. So our first idea in this case, and an idea that's often been thought of for batch reinforcement learning, is to build a predictive model. So the idea in this case was that we could take our old data and we'd build this statistical machine learning model of player behavior. And then once we have that, we can just treat it as a simulator. So just like I mentioned at the very beginning, once we have a model, we can move back to planning and treat whatever model we've learned as just the model of our MDP, and then do standard MDP planning to try to compute a policy that optimizes the performance, assuming that model is correct. But we ran into a couple challenges. So the first one is something that is probably known to all of you, which is the models are often bad or they may not be accurate. Now this is somewhat straightforward. You know, we have finite amounts of data. The models aren't going to be terrific. If the models aren't terrific, we're not going to have great estimates of how well the policy is going to do, just because we have error in our model, and that error can compound over time. This is what we didn't expect when we were first looking at this problem. So this was more concerning to us, that actually more accurate models can leave worse performing policies. So this was a bit surprising to us. It later became, as often is clear, much more clear in hindsight. But let me just tell you what's being shown on this graph. So remember, we have these 11,000 trajectories of player behavior, and we're going to build a statistical model. And what we're going to do is we're going to build the statistical model. In this case, it was using neural networks. And then we're going to treat that as the sort of world environment in our Markov decision process. And then we're going to do MDP planning. And so what you can see here on the x-axis is sort of the number of states we were using. I guess in this case, this must have been one of our tabular models to represent the world. And then on the y-axis is the normalized score. So the gray line there is the log likelihood. And this is log likelihood on a held out part of that 11,000 data set, 11,000 student data set. And so what you can see here is that a more complex model is better at modeling the world. We get better estimates of the student, of predicting student performance and behavior if we have more states. 20 states is not a particular complex model. And so you can see here that the log likelihood is going up as we use a more complex model. What the second thing is showing us is if we were to actually take this and get an unbiased estimate of how good that policy was, if we had taken those more complex models and plugged them into our MDP as a simulator, we actually get worse performance over time. So we're going to get worse performance if we use these more complex models, even though they're more accurate. So this was surprising to us. We were sort of concerned. We were thinking, well, in general, we want to have good models, and if we have good models, we should have good policies, but that's not always true. So, as I mentioned in a lot of the prior theoretical work, the idea is that if the model is good, the policy is good. And those things like the simulation lemma and provably packed results often rely on this. The key challenge here is that the model class may be wrong. So if we build a model of how people play or patients behave, etc., and we assume that is Markov, and then we use Markov decision process planning techniques to try to optimize that model, if the world is not actually Markov, then we will get very bad estimates of the value. So this is sort of obvious in retrospect, but I think it's something that can be very easy to overlook, and is an observation that was first noticed, I feel, at least to my knowledge, in 1995 by Andrew McCullum, where he noticed that even if you could write down a representation that would allow you to optimally represent the optimal policy, it might not be sufficient for learning the optimal policy, and it's exactly the same insight as here, which is that the system may not be Markov underlying that particular state representation. So if we take these models that we build and then we use them for planning, and the models are wrong and we use them assuming they're Markov and they're not, then we're going to get bad estimates of the policy even if we had quite good estimates of the predictive performance. And this relates to a lot of different problems that are, I think, coming up right now in things like simulation to real scenarios or adversarial examples, where what we're trying to start thinking about is what if some of our assumptions about how we're modeling the world is wrong, and how can we make policies that are robust to that? So some of the prior work takes this approach where what we're going to do is build these models of the world and then build a policy that tries to optimize with respect to that model. And one of the benefits of this is that you can get really good estimators of how well the policy will do. It's just that they might be totally wrong. So they're very low variance estimators. You don't have a lot of uncertainty in them, but they may just not be at all correct. And in fact, they're not consistent. If your model is incorrect about how the world works, then they can be biased even if you have an infinite amount of data, because you're just not modeling the world in the way that it actually is, and so your resulting policy estimates will be incorrect. So the key challenge here is also a distribution mismatch in terms of why this problem is hard. So again, we have these rewards, and we're going to have a policy in this case that is either mapping from states to actions or histories to actions. And so if we think about the distribution of outcomes that we would get under a particular behavior policy, we might get something that looks like this, which would allow us to, once we have that distribution, compute the expected reward for that behavior policy. But the problem is that for any new policy, we expect a different distribution over outcomes, a different distribution over trajectories and rewards. And given that, it's unclear how do we directly use the old data to figure out what that new distribution looks like and what its value would be. So that's where importance sampling comes in. And to my knowledge, Doina and her colleagues were the first people to introduce using this for reinforcement learning, but the idea has been around for a lot longer. And the idea is that we're going to take our historical data and we're going to reweigh it. Many of you are probably familiar with importance sampling, but just as a refresher, essentially what we're going to do is we're going to change it so that we upweigh the samples that look more like things that we would get under our new policy and downweight the samples that look less like what we would get under our new policy, where we assume that we have direct access to what is the probability of taking an action under the old policy as well as the probability of taking an action under the new policy. And the nice thing about doing this is that then we can map from our estimate of the behavior policy to our evaluation policy, the policy we actually care about, just using our exact data. Now, there's a number of nice strengths about this. It gives us an unbiased estimator of the policy performance under some mild assumptions about the differences between the evaluated policy and the behavior policy. And it's also strongly consistent under those same assumptions. But the weakness is that this can be an extremely high variance estimator. And in fact, there's been a lot of work on trying to couple together importance sampling style approaches with other methods to try to reduce the variance of these estimators, including some recent nice work from Remy Munoz and his colleagues called Retrace. But these have really been focused on the online setting, sometimes directly also for policy search, other times in the model-free case, rather than thinking about how do we do this in the offline case where we're limited by the data that we currently have access to. So in our case, the importance sampling estimators were not that high variance. We had a very short horizon in our problem. People typically play this game for only around 3 to 10 levels, and so the horizon is not that large. And so we could use importance sampling directly to try to find a policy that had 30% higher engagement. Now, there are two reasons why I like this particular example. One is that I think it illustrates the power of reinforcement learning, because in this case, when we actually evaluated the existing policy that was being used to teach students in this case, it was actually estimated to be having worse performance than random. So there'd been some human designers that had come together with a policy that they thought seemed pretty good for teaching students during this game, and in fact, that was worse than just randomly selecting levels for students. Now, that's not to say that those human designers were dumb or were just being silly. I think it just illustrates that in some of these settings, we don't actually have very good human intuition about what should be the optimal policies, and that's somewhere where reinforcement learning should really be able to help us. The other thing that I like in this example is that we could look offline for those 11,000 students and find this policy using importance sampling that we thought would be 30% better, and then we could validate it by running with another 2,000 students where we really did find that the engagement was about 30% better. So just a nice example of where we actually can be doing this offline counterfactual reasoning to try to find out better policies, and then those results really do validate when we deploy them. Now, to get to that aspect a little bit more, I think in many cases we really want to be able to have high confidence in the evaluations that we do, because we want to be able to ensure that before we deploy something new that it's going to be good, or that we have some guarantees on its performance. And so some of the work that Phil Thomas has done with his colleagues is thinking about this high confidence off policy evaluation, where again, we're limited by the existing data that we have, and we want to figure out how good is a new potential policy, and we want to have some high confidence lower bound on its performance. So in particular, when Phil started doing this work, he was interning at Adobe, and they wanted to figure out new ways to do things like customer marketing, but they didn't want to deploy things that might actually do really badly. And as I just told you, in the case of importance sampling, often we have very high uncertainty on the values. And so what they wanted to be able to do in this case is to get guarantees that the new policy with high probability would be better than some lower bound, where you could easily pick that lower bound to be the performance of your existing policy. So the idea in this case is to say, well, maybe we can have our estimates from importance sampling, and then we can use things like Hofting inequality to get a bound on what is the expected value. So we have a series of xi's, which we're going to assume are independent and identically distributed. And these could be, for example, our importance sampling estimates of the evaluation policy performance. And then once we have it, we can get an estimated expected value of our new policy by using Hofting inequality to compute a lower bound on the policy performance. Now you can see there that I've highlighted B in red, and B is an upper bound on what is the potential range of our variables. And one of the problems here is that in importance sampling, they can be very, very high variance, which means that value B can be extremely large. If you think about importance sampling as involving these products of probabilities between the behavior policy and the evaluation policy, then if things are very, very unlikely under the current behavior, but they're very likely under the potential policy you want to evaluate, then you can get very, very large numbers by taking that product over time. So if you see a very rare trajectory that now your new policy would say they want to take that most of the time, you can get extremely large numbers for B under those situations. So one of Phil and his colleagues' insight was that we could change the way that we compute some of these importance sampling ratios and still maintain a lower bound, and that this would allow them to be much more data efficient. So in this case, you can see that we have between 0 to 20 million trajectories inside of the data set. And you can see where the lower bound would be under different forms of lower bound. So we have lower bounds based on empirical variance, as well as several others. And what you can see here also is that that red line is the current behavior policy, its current value. And we want to figure out when can we be confident that the new policy would be better. Essentially, in Phil's work, what they do is they truncate the potential importance sampling weight to be no more than a fixed amount, which allows them to get a much tighter bound on the range of the variables they're considering. And that allows them to still preserve their lower bound guarantees and greatly reduce the amount of data that they need in order to ensure that a policy will be better. So 2 million trajectories is much better, but of course in a lot of high-stakes situations, 2 million would still be challenging. If in things like customer services, this is a very reasonable number, in things like healthcare or education, this would still be high. Another way they then sort of develop this further is to say, well, how could we do this iteratively? How could we do sort of high confidence policy improvement by leveraging these confidence intervals? And here, some of the work they did ended up using approximate confidence intervals instead of things with high probability, which allows you to get much better data efficiency at the cost of less confidence. And the essential idea here is that you could do this whole thing iteratively. You can first take your existing data, you can get a policy that you think with high probability is going to be better, or that you have some level of confidence in being better, and then you can take that, deploy that policy, and then improve over time. Now, what you can see here is that over time, it's very quickly getting much better. BCA in this case is using bootstrap confidence intervals, which allows them to be much more data efficient. And they can get this case where you're getting sort of monotonically, with high probability, monotonic improvement. So this will likely generally suffer a little bit compared to doing just generic reinforcement learning from scratch, but in some ways it's moving to us more towards this notion of safe improvement, because what it's allowing us to do is to be sure that the policies that we deploy over time are going to be generally getting monotonically better, which means it might take us longer to get to the optimal, or maybe in fact we'll get to a different optimal, but along the way we're not likely to suffer big losses. One of the things I want to point out about this case is that this work is very nice, but it's still dealing with problems that are generally quite small in the domain horizon. So I'll pause in just 10 seconds, but I'll say that so far we've talked about two extremes of this offline reinforcement learning case, where we've been thinking about there being a model and then using it as a simulator and to do planning. And the benefit of that is it can be very data efficient, but it can yield biased estimates. And then I talked also about using importance sampling approaches, which can be very data intensive, but they're unbiased. And what we'll talk about after the break is to talk more about batch reinforcement learning and then move on to how humans can help reinforcement learning systems. So we'll take about a 15-minute break now, and then we'll resume. Thanks. All right, so what I was saying before the break was that we were thinking of these two different ways of doing offline reinforcement learning, one of which that had a lot of bias, or could have a lot of bias, and one of which had no bias but might not be very data efficient. And one of the many amazing things about statistics that has come out of that literature is doubly robust estimation, which essentially combines ideas from both of these. So the idea is that we can have estimators that combine between the benefits of model-based approaches and importance sampling-based approaches. So doubly robust estimation has been present in the statistics literature for a long time, and to my knowledge, the first people to bring it over to the control and decision-making community for multi-arm bandits was by Miro Dudek and his colleagues in 2011. And the idea of a doubly robust estimator, and again, this may sound familiar to a lot of you that have been doing some work in policy search, is that we're going to have an estimate in this case. So right now we're in the bandit setting, just to be simple, where we're going to have a model of the reward. So this is our model base, that's the R hat. And then in our actual data, we're going to have rewards that we actually received, and that's the R. And then we have our importance sampling ratio, which allows us to compare what is the likelihood of us taking that action. Again, in this case, this would be a fur bandit or a contextual bandit, under our desired policy pi 1 compared to the behavior policy pi 0. And then the V hat here, all of the hats are indicating what we're getting from our approximate models. So here, this is the value of the state under our approximate model. So the doubly robust estimator combines these, and we can also think of it as a control variate type approach, which has been very popular in policy search recently, to try to combine between the benefits of a model-based approach and importance sampling. Then in 2016, Nan Zhang and Lihong Li extended the notion of doubly robust to reinforcement learning, which we can again think of as there being a model that we use to compute the value function and to compute a Q function, as well as the actual rewards that we have from our underlying data set, and we can weigh those by our importance sampling weights. And again, in this case, we're going to try and blend together between the benefits of the model-based approach and the values we get out of that, and the importance sampling-based approaches. And these methods allow us to try to get to the best of both worlds. However, one of the limitations of this original doubly robust estimator is that the estimator that was derived was still designed to be unbiased. And unbiased estimators can be great, but they can sometimes still have very high variance. And one of the things that we did last year was to argue that in some cases, we may care about just having very good empirical estimates of how good our policy is, things that we might quantify with a mean squared error, so that we're willing to trade off a small amount of bias in order to get enormous reductions in variance. So again, the idea here is that we have this model-based estimator with high bias and low variance, and another importance sampling-based estimator with high variance and low bias. We want to blend these. And in particular, we can think about there being sort of a whole continuum, where you could imagine that we could use either the model to estimate the rewards for most of a long trajectory, or we could use the importance sampling to estimate the rewards for most of the trajectory. And we can blend across these. These gives us different step updates, where essentially you can think of there as being different blends between starting with either the importance sampling and how long do we continue this for, versus the model. And the idea here in this case is that we can directly quantify what the bias and variance of these various blends are and treat it as a quadratic programming problem, and yet still end up with an estimator that is strongly consistent. So the estimator we compute in this case, which we call model and guided importance sampling, is not going to be unbiased, and it's not going to be unbiased on purpose so that we can try to get to estimators that are much more efficient. And so what we can see in this case in some of our small simulated domains is that we can get orders of magnitude tighter estimates from the same amount of data by doing this trade-off. We also investigate in this case looking at things like weighted doubly robust estimators. As some of you are probably familiar, weighted importance sampling is often have much reduced variance compared to importance sampling, and we can show a similar thing by extending doubly robust to the weighted doubly robust setting. We can also extend this approach to when we actually are trying to do policy selection by using this new estimator to guide which policy we deploy. So one of the things that we noticed when we were trying to do this is that we were thinking back to some of the application domains that we care about. This is a fractions tutor. I'll just give a brief aside of why I think about fractions so much in my applications. So in the 1980s, there was a fast food company, it's still around, called A&W, and they were doing a new campaign to try to compete with the quarter pounder hamburger. And so they decided to roll out the third hamburger, the third pounder. And they did all these taste tests, and people loved the taste, and they were really excited about them rolling this out, and they made it the same price as the quarter pounder, and they thought it was going to go great. And so they rolled out their third pounder, and it totally flopped. And the reason it totally flopped was because most Americans said, why would I pay more for less beef compared to the quarter pounder? And so as several of you who are chuckling are noticing, a quarter is in fact smaller than a third. And so this is a major issue with a number of Americans understanding our fractions. And unfortunately, a lot of the recent research suggests that we have not progressed that much in the last 30 years. So fractions is really important. It turns out that it's a critical skill if you want to learn things like algebra, which I would argue is a very important skill, even if you don't want to go up to things like calculus. And so a lot of our tutoring systems focus on fractions. Now, in these kind of cases, we do actual classroom studies with students, and so we have these captive audiences for maybe a week or two, and in this case, students really do a large number of problems. They might do something on the order of 20 to 100 problems. And the challenge is that if you're using an importance sampling at all for these type of approaches, typically the variance scales exponentially with the time horizon. So you could imagine that if you get to something that's, has a 100-step time horizon, it's going to be completely infeasible to get good estimates out with standard importance sampling. And so what that means is that even using some of the estimators I just described, you'll just end up relying on the model because you just don't have enough data to fit them. So one of the papers that we're presenting on Wednesday is going to be thinking about how do we leverage hierarchical structure and other structure to try to get around this problem and try to tackle how do we do off-policy evaluation when we do have long horizon problems, because that really does come up in a lot of different challenges. And the insight we had here is that we can explicitly think of decomposing a trajectory into a first part and a second part and looking at what the covariance is between the importance sampling weights of each of those parts. And if we can decompose this, we can think about just dropping the importance sampling weights of the first part, and if those are really decoupled with the second part, we don't lose anything, and if they are coupled, then we can bound the bias that we introduced. There are other places where, like when you have hierarchical policies, where this type of decomposition can happen very naturally, which allows us to get an exponential improvement in the variance of these type of estimators compared to what was possible before. So one of the places we looked at that recently, just as a simple example, was looking at breakout. And we also extended this estimator called INCRIST to WINCRIST to tackle the weighted approach for this. And one of the things that I'm excited about in this case is these are small policies. It was just a proof of concept, but as those of you who are familiar with the breakout game, it's a long horizon problem. In this case, we're looking at a 200-step horizon problem, so far more than what we could have done before. And we compare a policy that was learned after 20 million time steps versus after 40 million time steps. And we find that using that 20 million time step data, where they have a reward of about 5 over those 200 steps, versus the 40 million horizon data, or 40 million time step data, where you have a performance of about 5.4, that in fact we can get estimators that are tight enough that we can basically distinguish between those two. So with the data that we have in this case, even though it's over a 200 time step horizon, we're getting tight enough estimates in our mean squared error that you actually might be able to distinguish between these type of cases. So I think that this sort of scenario of how do we get estimators that directly trade off bias and variance can help get us much further to be able to tackle a lot of the problems we want to. There's also a lot of interest in general of how do we get other sorts of high confidence bounds for these type of estimators, including some nice work that's recently come out of Peter Stone's lab. I'll just add something sort of as a cautionary tale from some of the work that we've had before I get too excited about all this stuff, which is if we are using importance sampling estimators, even the ones that I just mentioned, there can be problems when we start to do policy selection. So even though the IS policy estimates are unbiased, once you actually use them to make decisions about which policy to use, they can start to be unfair. So this is work that was led by one of my graduate students, Cheyenne Doherty, and what we're defining as unfair here is that we're choosing the wrong policy as having better performance over 50% of the time. And the reason this can occur is essentially because you can have very, very different variances across different policies based on the data that you collected. And so that can mean that you systematically are biased against some policies that are further away from your behavior policy, which can mean that you end up making bad decisions. And in particular, we see that this can be a problem in terms of overly penalizing algorithms or penalizing policies that can be less myopic or have longer trajectories, which are often the ones that we might like. So this is one of the challenges that we've identified from just using importance sampling, even within part of other algorithms that might be using model-based. So in some cases, really, the horizon is long, our data is extremely limited, we're not in Atari, we're with students, we've got 1,000 students data, which is quite a lot for running classroom studies, but nothing in terms of reinforcement learning. And so we still have just way too high IS estimators. So another approach in this case is to think about essentially doing robust model evaluation, where you can think of there being a suite of different models that you're considering, and you try to make policies that are going to be doing well, no matter how an adversary might decide which policy or which world you're going to run in. So for example, in our case, we've thought about this for situations where we have students from many different school districts, and we can build models of student learning and performance in each of them, and we want to get a policy that does really well for all of the school districts, even if we are even if we don't get to choose the type of students that end up using this policy. Now, I think I am sort of bringing us back to models at the end here, and I think that at the end of this section, and I do want to highlight that I think models can be really powerful, but knowing which models to use can be very challenging. As we saw before, if you think your models are Markov and they're not, that can lead us to challenges in terms of this policy evaluation. And I'll just highlight something I said before, which I do think that Bayesian neural networks could be really promising for this. One of the reasons that I'm excited about them, though we haven't done work on them yet, and I know other people, like particularly Fanali Velez's lab has been doing, is that they allow us to have an explicit representation of our uncertainty about the world and our uncertainty in the model, and yet have very flexible parameterization. So I think that they could be a really interesting place to start to continue to explore how to do this off policy evaluation. All right, so that's going to conclude sort of a lot of the technical challenges, or at least some of the important technical challenges that come up when we do reinforcement learning for people. And so now the last part of my talk is going to be talking about RL by the people. So how do we leverage people to try to make our RL systems better? So there's a number of different ways we might be able to leverage input from people in order to make better reinforcement learning systems. And I'm going to steal this nice sort of overview from Taylor, Kamara, and Hayes from a section of their nice tutorial on interactive machine learning in terms of how I'm doing the sort of designation of a number of these different ways we could think of human input. So now I'm going to go through sort of a number of different ways we might imagine this could occur. So one natural one is human writes down a reward function. Now, there's a lot of issues even immediately there. What reward function should they write down? Do you want to write down your true reward function, or do you want to write down a reward function that might reflect limitations of the agent that you know about? And do you want to be able to write down things that will allow us to have constraints on behavior compared to just maximizing reward? So we may want to be thinking carefully about what is the objective function for we want the agent to be maximizing and how we best encode that, and how do we think about bounded rationality or other forms of computational constraints on the agents. So one nice work on this that is coming out at NIPS right now is from Berkeley, from Dylan Hatterfield-Menville and a number of his colleagues, which is thinking about inverse reward design, which means that we can leverage the rewards that are designed by people, but without having to assume that they're perfect. So who here has heard of King Midas before? Okay, so a few people, but not all. So King Midas is sort of from Greek mythology, and the idea is that at some point he wished that he could turn everything he touches to gold. Seems like a good idea. Gold was really valuable. But of course, that's not exactly what he wants, right? Like he still wants to be able to eat. So he doesn't want to have to, as soon as he touches an orange, the orange becomes gold. So he can no longer eat anything. If he touches water, that becomes gold. So in fact, the reward and his desire that he expressed is in fact not what he wants, even though it seemed like a good idea. And so the idea of inverse reward design is to say that the reward is an observation of the true desired reward, but it's not necessarily the true desired reward itself. So we can compute a Bayesian posterior over the possible true rewards that the specifier might have meant. And then once we have that sort of distribution of rewards, then one can compute a risk-averse policy with respect to that. So this can have some very nice behavior in the sense that it can avoid new bad things. If there are things that we're really not sure that how the reward designer, whether they would like it or not. So let's say we see a new feature like hot lava, and we've never seen the person talk about hot lava in any of their reward function. Generally, the agent will avoid hot lava because it will be risk averse towards features where it doesn't know the reward well. One of the limitations of it is that it also avoids new good things because of this risk-averse behavior. But I think it provides a nice way to have, again, towards more safe reinforcement learning, where we could leverage the input from a human, but still be sensitive to the fact that they may have ill-specified some parts of things and try to be risk-sensitive towards that ill-specification. Now, another challenge if we want people to write down the reward is that it might be hard for us to specify the reward. So if you're asked to write down what is the reward function over the features, if you're doing surgery, I think it would be really challenging. It would be hard to write down all the features that people think about and what the relative rewards are and trade-offs while doing open heart surgery. But there might be other ways to encode that, or there might be particular things that we could leverage and use them as sort of potential shaping, or do reinforcement learning on top of a partially specified reward. Now that brings me to the second thing, which has been hugely influential, which is having a human provide demonstrations. So in the context of surgery, this could be very reasonable, and there certainly is a lot of interesting active work going on surgery of how would you take the demonstrations from experts and then use them to try to create a policy. This has been known by many different related names and areas, things like imitation learning, inverse reinforcement learning, learning from demonstration, and apprenticeship learning. And it's really been hugely influential, particularly in robotics, since basically 2000. So in this particular case right now, we're going to assume that we get access to an initial set of trajectories and then have no more interactions with the person. So when I say learning from demonstration, I'm going to assume that we get a fixed set of demonstrations to start, and then no more demonstrations from the person. And the goal is to learn a good policy in this setting. So one approach to doing this would be to treat this as a standard supervised learning problem. We're going to have mappings from input states to actions as demonstrated by the person, and we would just try to use supervised learning to build that mapping up. The limitation of that is that our data is not IID. The series of states that we reach depend crucially on the decisions that we make, And so, as observed by many, including by Drew Bagnell here, if you follow the policy that you get from doing behavioral cloning or using supervised learning to induce a policy, then you may encounter parts of the state space that are very different than what you received in your original training data. And you can end up having very bad performance because of the fact that the data that you get in the future is going to be generated by a different distribution than it was generated in the past if your policy has changed. So because of this, there's been a lot of interest in different variants to try to tackle this. In particular, inverse reinforcement learning has been hugely influential. The idea in this case is that we're going to try to directly understand what is the reward function that a person was using. And typically, we're going to assume that we have access to a dynamics model or an ability to try new policies online. Now, inverse reinforcement learning is fundamentally ill-specified. If you're trying to figure out what reward makes a policy optimal, setting everything to 0 is always sufficient because any policy is optimal if you never get any reward. So there's been a lot of work to think about how we should try to break ties in these scenarios and what sort of prior information we should use to kind of shape what are the rewards we learn from demonstrations. One of the big ideas here has been to try to match the state features. So to say we want to get a policy out where the distribution of states we reach looks similar to the distribution of states we reach under the observed demonstrations. The idea of max entropy has been very influential. And there's also been a lot of interest in meta-learning in these cases. People have also often done reinforcement learning on top of this, as we'll see in the next case, because there's been a lot of interest in doing this, combining these ideas with deep learning. So in particular, there's been some very nice recent work by Chelsea Finn, Sergey Levine, and Peter Abiel looking at guided cost learning. With the idea is that we get these demonstrations, but then we're going to continue to do reinforcement learning as well with these. And by combining these two, we can end up getting some very nice performance in the context of robotics. Similarly, some related work by Stefano Imran and John Ho has been thinking about generative adversarial imitation learning. And in there, just like some of the work in Chelsea's work that I just mentioned, we've been thinking about the fact that what we ultimately want is a good policy. We don't actually care directly about the reward that is being demonstrated by the person, but we want to be able to get a high-performing policy eventually. So in Gale, the idea is that we get access to an initial set of expert trajectories, and then from there, we're going to try to directly figure out a way to get a reward function that is indistinguishable from what we think is happening by the experts, and use that within the context of TRPO to try to get a good policy. And what they have found is that they can, on a number of different control-like tasks, that we can do much better performance than things like behavioral learning and other forms of other forms of baselines. And in some cases, we can even get better than experts because we can continue to do reinforcement learning on top of this, and we're not constrained to always have to be close to the expert. So learning from demonstrations, I think, is an enormously exciting direction. I think there's some challenges to it, particularly when we start to think about using it for people-focusing tasks, but I still think it's a really very, very promising approach. So we do need access to experts doing the task. If we do reinforcement learning on top, we can be more robust to if people aren't experts. And there's been some nice work by Matt Taylor and Sonia Chernova and some other people to look at if you have variable quality in your demonstrations. But if you are doing it in the case where you don't have experts, then it's particularly important to be able to do online reinforcement learning, which is not always feasible. In the case of things where we're sort of interacting with people directly, like patients or students, it may take a very long time or be infeasible to collect these form of trajectories. So if we want to optimize student performance across years, that could take a long time, or providing customer recommendations across many months. And it also, most of these approaches have focused on providing us with local guarantees. So they don't necessarily allow us to teleport and get to really radically different solutions. And if we want that, then we're going to need some way to handle the exploration-exploitation trade-off online. There's also a really important issue of just how we write down the problem in these settings, how we're going to write down the state features. I think this is particularly important in things like healthcare and student modeling because it's not always clear what set of features we should even be writing down. And even whether we should be modeling it as a POMDP or an MDP or a bandit or else otherwise. And I think one challenge historically in this is that we've often suffered a cost if we model things in a more complex setting than what we actually need. So certainly on the theoretical side, we don't want to model something as a partially observable reinforcement learning problem if it is in fact a multi-armed bandit. But some of the work we've been doing recently on the theoretical side has been looking at how can we create algorithms that actually inherit the problem-specific bounds of the problem when we deploy them instead of the way that we encode them. But just to summarize for the learning from demonstration part, I think that generally it's extremely promising, and it's particularly great for sort of automating and scaling up and fine-tuning good solutions. And I think that we'll see a lot more really exciting work on this in the next few years. So another thing, and the next few approaches will be more in this line, is really keeping the person in the loop as the agent is learning. So instead of providing a reward function in advance or providing demonstrations in advance, the human is going to continue to be around as the agent is learning, so that it's really an interactive process. So one of the early works that I know in this space was done by Andrea Tomás and Cynthia Brazil, looking at how can a human provide online rewards to an agent while they're learning. So in this case, there was a little robot, an artificial robot in a simulator which was trying to learn how to cook, and people could provide positive or negative scalars about the actions that the robot was taking. Similar, the Tamer framework, which came out of Peter Stone's lab and was led by Brad Knox, has thought about, again, allowing people to provide positive and negative reinforcement. This sort of idea is typically thought of a lot in the context of things like animal training, that you give your dog a bone for doing certain good behavior and not if they don't. And so the idea in this case is that we can be using online reward to try to shape the behavior of the agent that we're trying to train. Another idea is that rather than providing direct reward signals, maybe it's easier for people to provide direct advice or labels or feedback on the decisions that are being made by the agent or the decisions that the teacher thinks that the agent should perform. So Drew Bagnell and Stefan Ross and Jeff Gordon developed the Dagger algorithm a few years ago, which is very similar to inverse reinforcement learning, but it keeps around the idea that you can continue to get feedback from the expert as the agent is learning. So as I mentioned before, when we are trying to deploy a policy that maybe we learned from supervised learning, we may encounter states which are very different than in the distribution of data that we previously collected. So in this case, what Dagger can do is it can ask the human expert what the agent should do in those places, providing that pi star. And so that means that we're getting an increasingly large data set of the agent getting labels from the expert on the states that it's actually encountering as it's trying to start following this more optimal policy. There's other approach on policy advice, which similarly imagines that people are giving advice to the agent periodically about whether or not the agent took an action that was correct. And that people may not be perfect in terms of the feedback they're giving, but that they may periodically provide somewhat noisy feedback about whether the agent is currently taking good or bad decisions. The idea in this case is that then the agent can combine this with their own experience in order to hopefully speed learning in these type of tasks. So Dagger and these sort of policy advice approaches are arguing that maybe it's easier for people to provide direct feedback for individuals, feedback for the agent based on actions. But I think that there's some strengths to this and also some limitations. So the strengths are that often you can get substantial performance gains from doing this. The challenge is that this can be extremely expensive, because essentially you need to have that human in the loop over time as the agent is learning. And I think, to me, that's one of the reasons why this hasn't seen quite as much amplification as the work in learning from demonstration. Because if you have learning from demonstration, you can just collect these data sets offline, or you can have access to how people are already doing these tasks. Whereas in this case, you really require an agent to be around you really require a teacher to be around during the agent's learning. However, I think that as we continue to have situations where we're interacting more and more with interactive agents, this scenario could start to be more realistic. As we start to have robots in the home, or as we can interact with chatbots, it could be much more reasonable for us to teach the agent over time and provide periodic input about whether or not we like the decisions that are being made from the agent. I think there's also a lot of interesting merge cases where you could imagine sort of doing learning from demonstration in general and then periodically giving feedback to the agent if it gets really stuck, or for the agent reaching out to a teacher in those cases. The other nice thing about having a human in the loop continuously as opposed to just in the beginning is that it can help in terms of having the human be able to identify if something is going radically differently than what the human expected. So if, for example, the agent has learned a local policy that was not the policy that the human desired, then if you have the human in the loop, then they could provide that policy feedback over time or react to non-stationarity. Now, these so far have assumed that either people are providing sort of a generic reward structure about the optimal reward in advance, or providing expert demonstrations, or maybe trying to provide direct feedback about what's the right thing to do or what's a good reward for it. But it's not always clear that that's how people want to teach agents or whether that's how people should teach agents. So in particular, at least for animal training, there's some results from Michael Littman and a number of his colleagues that indicate that when people are providing reward feedback, they may assume that the agent is interpreting that as action information. So the idea is that if I provide, a positive 1, then I might think of that, I might assume that the agent is interpreting that as I am taking the right action, not as if that is actually a +1 in terms of my reward function. And those two things are different if the agent is in fact trying to optimize its long-term reward. So if the agent is trying to maximize its long-term reward and it thinks of this local rewards as actually being the true reward signal, then it can end up sometimes being distracted by local rewards rather than following the true optimal policy if the human actually thought that they were demonstrating the optimal policy. Another thing is that people can perform the task very differently if they think they are trying to show the agent something versus merely trying to demonstrate how to do the task with a very high level of performance. So when we typically think of learning from demonstration, we think of people providing expert ways to do a surgery or good ways to pick up a cup. But when people teach how to do a surgery, or they teach someone how to pick up something or do a complex maneuver, they often demonstrate in very different ways than what they would do if they were merely trying to do the task for a very high performance. And this sort of information is in fact known for human teaching to be very effective. So for example, if you're trying to teach various forms of medical procedures, then it can be very helpful for people to see both expert performance and novice performance if that they are given labels about which is which, so they can help learn what is the correct way to generalize and what are things that are considered negative examples. In addition, there's recent work from Matt Taylor and Michael Littman and others that suggests that some of the assumptions that we make about when we're typically designing learning from demonstration policies is incorrect. That often when people are demonstrating or reacting to the learner, we're keeping in mind the learner's current policy or our estimate of the learner's current policy when we interact. And again, this is quite similar to, I think, what we see in a lot of human teaching, that we often build models of the person that we are teaching, or in the case of coaching, of an athlete, and then we're using that to guide what type of feedback we give when. And so we are not ignoring the state of the learner, but in fact, we're trying to directly react to the state of the learner. So as a nice example of some recent work that's kind of in this vein is cooperative inverse reinforcement learning, which is a paper from Anka Dragan and Peter Beal, Stuart Russell, and Dylan Hudfield from last year at NIPS. And the idea in this case is it points out that the way that we should demonstrate should depend on what the capabilities are of the agent that is going to be doing this task. So for example, it might be that if you're trying to build two different types of widgets, maybe you're trying to build scissors and you're trying to make paper clips, that your own capabilities are such that the optimal policy for you is different than what the optimal policy would be for the robot that might have different capabilities. And so then when you're doing demonstrations for the robot, you shouldn't demonstrate the optimal policy given the humans. For the human, you should demonstrate the optimal policy given the capabilities of the learner. So they thought about this for some particular cases where they were trying to provide instructive demonstrations, provably instructive demonstrations, by thinking of this as a two-player cooperative game, where in fact both sides are going to be rewarded by the same reward function. And I think that this type of framework is really powerful to start thinking about how can we do much better than both the adversarial setting or even the expected setting by thinking about direct models of the other. So I think that there's been a lot of really exciting work in this general space. There's also a lot of really exciting work on machine teaching. And there's a lot more potential areas there where we could be leveraging people to try to improve reinforcement learning systems. I want to add in a little bit of another way that I think that we could think of people as trying to teach the system. So this is a histogram tutor that we developed a couple years ago. And in this situation, we wanted it to be a continually improving tutoring system. So we wanted like a student to interact with this histogram tutor, they'd get some problem, we'd see whether or not they got it right or wrong, and then at the end they'd do a post-test. And the idea was that we do this not for a single student, but we do it across many students. And what we found is that over time, the tutoring system stopped giving some of the problems to the students. So in this case, its objective was to maximize the post-test score divided by the square root of the number of problems given. And we designed this objective function to try to balance between maximizing post-test, but doing so in an efficient way. And so what we found is that over time, it just stopped giving some of the curriculum. We thought that was a little bit strange because we knew that that was curriculum that students needed to learn in order to do well on the post-test. But in fact, what the system had done is it self-diagnosed that the problems weren't helping people learn. So essentially, the action space was insufficient. So just like if you realize you're taking a class and the lecturer is completely ineffective and you stop going to class, it's exactly what our tutoring system had learned. It had learned that the content that we had was not helping teach students, and so it was better just to bypass that content altogether and go straight to the post-test. So, of course, if we were in a fixed setting where we couldn't change how the world works, then we'd be stuck. There wouldn't be anything else that we could do. But this is one of the nice scenarios where people are very different and people-facing systems are very different than games. So in particular, humans are invention machines. If the Zika virus comes along, we don't just say, that's really too bad, we don't have any vaccines for the Zika virus. We invent new actions. And similarly, if we want to observe new phenomena, we invent new sensors. And so I think another way that humans can help reinforcement learning systems is by expanding the specification or expanding the space. So this is another way to think of having humans in the loop, where we can have additional people being able to add new actions into the system and do so in a way that is driven by the agent itself. So one of the ways that we first started to do this was thinking about this for how we could direct the human effort to add new actions. Now, of course, as many people in the audience know, if you do have a system that isn't performing in the way you want to, you do change it. It's just that the system itself may not proactively tell you when that might be needed. And that's one of the things that we're trying to do here. So the idea in this case is that we tried to reason about what part of the state space to ask for the agent, ask for the teacher to provide new actions for, based on an estimate of how much that could improve the potential value function. So we're sort of trying to get an estimate of the expected local improvement in utility of the value function if we were to add in new actions. And one of the nice things we can see in this case, and this is a simulated situation, but is that even if we're only periodically getting effective actions, we are doing reinforcement learning over this space, and so we can still benefit over time as long as the sum of the actions we're getting are actually effective. So we're using this now to try to tackle providing hints in a word problem generation, where the idea is that when students are doing these activities, they may need hints in order to do better, and maybe our hints aren't adequate. And so we can ask people dynamically about hints to add in order to help. A second thing we're trying to do is more about expanding the feature space. So often there are many, many different ways to model people, and there are a huge number of features we could collect. And maybe there are features that we don't even know are important. So the idea in this situation is to think about whether or not there might be a latent feature where if it was to become known, if we could make better decisions. So in a really simple example, you could think about just a 5x5 grid world where there are additional features about the cells which could be relevant to what is the optimal policy. So in this case, the initial world representation is just 9. There's 9 features, 9 states based on those black lines. And in this case, we can get a discounted reward of 0.4, and there's only 9 distinct states. But what we can do is we can learn and hypothesize whether or not there might be latent features that would allow us to make better decisions. And if there are, if we hypothesize that getting an additional latent feature would allow us to make better decisions, we can reach out to a human. So this is a simulated case, but you can see in this situation how we end up breaking apart the states over time in order to get a better representation that will allow us to make better decisions. And again, I'm personally very interested in representation learning, but I'm very interested in representation learning that allows the agent to learn to make good decisions quickly. And so this is part of the effort towards that. So as an example of these type of features, you could imagine maybe there are latent interests of the student, which if you knew them, maybe you could just ask them about it. Maybe it would make a very big difference to the type of activities you give them. But if it turns out that wouldn't be important, then you don't want to include them. So just in a high level, I think another way that people can help, another way people can act as teachers and can help reinforcement learning systems is to change the specification of the system over time. And they can do so in a way that is being driven by the RL system itself, proactively reasoning about where it could maybe benefit from improvement. Now, I'll just say one more thing about this, which is, so we started doing this experiment, and we tried to start having people in the loop make better hints, and it didn't do very much. So we tried another way of doing it, and it didn't do very much. And we were having graduate students in education create these hints, like they were smart domain experts, and yet the sort of additional actions they were adding to the system were not very effective. So I think what comes up in this case is, how do we actually teach humans to teach agents? So just like when a new teacher starts teaching at the beginning, they may not be the most effective instructor, and over time they learn how to be a good teacher. Similarly, when we have humans interacting with reinforcement learning agents, the way in which they're either providing demonstrations or trying to change the state space may not be very effective. This may be because the people don't have a good model of how reinforcement learning systems work, or they may not have access, for example, to actions that actually could change the state space or make the system more effective. And so I think in many cases, the people that are interacting with these systems also need guidance about how most effectively to interact with reinforcement learning systems, because really in many of these cases, it should be a cooperative interaction, and both sides really want to obtain high reward, but particularly if you're using domain experts that don't know much about reinforcement learning, then they may not be clear about how best to teach these agents. I think there's a huge number of open directions here. And I think this is important too, because when we involve teachers, it's still very expensive often compared to leveraging just past data. And I think it can be very powerful, but we need to be able to do it in sort of a judicious and cost-sensitive way. So I think that there's a lot of also really interesting questions here about how can we leverage information that we've got about previous teaching demonstrations instead of just expert demonstrations, because these ones might be exactly the ones that are more effective to help teach agents. There's been some nice recent work from Michael Littman's group and colleagues on this step, but I think there's a lot more to be done of how can we leverage demonstrations, of which we have a lot, as well as leveraging teaching. So that just summarizes some of the different ways that I think we can use people to try to make better reinforcement learning systems. I think there's still a lot to be done in this case, and things like machine teaching can also be very influential here, where we try to directly build models of the learner and then think about how we can best provide examples. So just to summarize, I think that there are a lot of applications that could really help people, that could benefit from reinforcement learning, and I also think there's a lot of ways that people can make RL systems better. We're doing a lot of this in my group. If anyone's interested in a postdoc opportunity, please come talk to me, and thanks for your time.
Thank you very much, Emma, for the really nice tutorial. There's a couple of microphones, so whoever wants to ask questions, please go to the microphone.
Hello, can you hear me? Okay, so I think there is a fundamental tension between data-driven learning and human expert-driven learning, right? In this kind of scenarios. Do you have any pointers on how do you balance those two?
I think it's a great question. I think that the question is saying, you know, how do we balance between direct experience and data-driven learning with the human experts? I think in some of the work that Andrea Tomaz has done, they've looked at just directly combining them, thinking of them as being independent sources, and so you can multiply those in. Other ways people have used them is to do things like action biasing. Some of David Silver's early work, they thought about this for things like Battleship. How would you have sort of preferred actions to bias the exploration? So I think there's a number of nice techniques to do that, but I think there's still a lot of question about what's the best way to attenuate that and how do you know when you should stop trusting the expert.
Hi, thanks for the great talk. And you mentioned some of the applications that have been used. Could you give maybe more samples of real applications, like not game related, but as medical field or like something else which has already been used?
I don't know everything that's happening. It's a great question. I don't know everything that's happening in companies. I know that there's a lot of interest in reinforcement learning now from a number of different companies, whether it's for things like customer recommendations, or I know that Siemens has been doing work on this for machine repair. I know that a number of my colleagues in the healthcare space are very interested in the off-policy case and have been doing work on that. Other people like Susan Murphy and Joelle Pineau have been doing work in the healthcare space for things like SMART trials, where you have some amount of randomization sequentially over time and then identifying patient treatment, or for things like epilepsy. I think another really interesting case is for using it for things like prosthetics and how do you do very fast adaptation for patients. There's a very nice recent science paper from Steve Collins' group, which is trying to do that for prosthetics, which I think is really exciting.
Hi. So one way to scale humans teaching agents could be to leverage crowdsourcing platforms. However, the quality is not under control, quality of the teaching. So what could be some ways to model the teachers' variations in how they teach or the quality of teaching?
I think that's a great question. So, and we've been doing some work on leveraging crowd workers to essentially provide actions that we can use to teach agents. I think there is some really nice initial existing work from people like Dan Weld and Eric Horvitz's group, looking at, and AJ Kumar, looking at how do you model crowd workers, and then you can imagine both modeling them as learners and teachers, and then trying to change that over time, your model, and figuring out how do you best teach them so they can get better over time, as well as which feedback to use to decide to teach new crowd workers, for example. I'm happy to talk about that more. That's something we're actually working on.
Okay. Nice talk. Thank you. So certainly humans are making decisions in real life, just like reinforcement learning algorithms. So in terms of understanding how humans make decisions, what people have done, for example, like how do people learn to make better decisions over time as reinforcement learning algorithms?
I think that's a great question. So there's the whole field of sort of reinforcement learning and neuroscience, both to think about what's going on in the brain when we're trying to learn things, as well as more on the sort of cognitive science side. I think I'll more just direct you to some of my colleagues doing that work. So people like Tom Griffiths and Josh Tenenbaum think a lot about how people learn to make decisions. Sam Gershman as well. There's also some really exciting work, I think, that connects that with the deep reinforcement learning, showing that if we start to think about agents that are reasoning at the object level and dynamically testing theories, we can get performance that looks much more like human performance compared to the standard DQN.
Thank you.
Hi. First off, thanks for the talk. So one of the problems I've been looking at recently is offline evaluation, which you talked about in your presentation. One thing in my specific problem setup is that we don't know what policies collected some of the data for our offline data set, which makes it hard to get importance weights for this kind of thing. So I was wondering if you had any ideas on, I guess, ways to get around this, or potentially like ways for offline evaluation without having to do importance sampling.
Yeah, I think it's a big challenge that with importance sampling, normally we're sort of restricted to the things in our current pool. I think that's actually somewhere where models can be hugely beneficial because they can allow us to generalize far beyond the experience that we have. The challenge is that often that requires us to make strong assumptions about the model being correct. But I think that particularly depending on the domain, if you have domain knowledge, like in the robotics case, then you can often make models where you can really generalize much further. And some of the work we've been doing recently is to try to see whether we can use deep neural networks to try to automatically uncover those sort of invariances and then use models to then generalize much more than we could with offline approaches.
Thanks.
Hi. First of all, thank you for the tutorial. It was a great talk. When we talk about reinforcement learning for people and by the people, an important question that comes up today is fairness and bias by the people towards other people, like due to this societal systematic biases that are. Like, do you have any ideas or pointers or views about the same?
Yeah, so I think there's a whole new effort on fair, accountable, and transparent AI and machine learning, which I think is super exciting, and you may be involved with already. I think in some of the work that we've been doing, we've been talking about ensuring that agents are well behaved, and in some of that, we've been trying to ensure agents will have properties like not over predict systematically for one group and under for another, or to try to guard against negative effects. But it doesn't tackle if there are sort of biases that we want to avoid that we're unaware of. I do actually think this is a real place where machine learning can show us as a lens for our society, and then it gives us the opportunity to systematically correct for some of those once we can identify them.
And also specifically about talking about safe exploration, or how like experimentation with people might affect them in adverse ways. Like, is there anything in that respect?
In terms of safe exploration, I think that's one place where the offline evaluation is very powerful, because then you're not experimenting on anybody new. I think the safe exploration work that I'm aware of has mostly been done for the robotics case, but I know it's something that many companies are very concerned about because you don't want to lose customers, and certainly for things like healthcare and education, it's very important. So I think it's a really big open question of how we can do that and what assumptions allow it to be possible.
Thank you.
Let's thank Emma one more time.